Okay, good morning, everybody. So there were a few announcements over the weekend. If you missed them, hopefully you didn't miss them because I actually sent email about them. So number one is that the labs this week are online again. I have to somehow get into Jeffrey 155 because they're locking it all the time. So I haven't actually been able to see what's in that lab. Hopefully I can get in there today and check out what's going on. If it's suitable for trying to demonstrate, if it's suitable for trying to demonstrate how to use Eclipse and how to program and things like that, I will transition to the in-person labs next week, but this week it's still online. It's actually a lot easier for me to do them online, but it seems like quite a few people want them to be in person. So I'm happy to do them in person. I'll see if I can actually stream the lab at the same time, which means I'm going to be giving a Teams meeting in a live person lab. So if you don't want to come to the lab, that's fine. Well, hopefully it'll be fine. I'm going to try to stream it at the same time. What else is there? The dates have all been set. So there's a midterm date now. There's assignment dates are all set. Only the exam remains to be scheduled, but that's because the exam office does it, not me. And other than that, we're good to go. So we need to spend one lecture talking about floating point arithmetic on your computer. Floating point is weird, right? So in Java, you have two floating point types. Right? There's one called float. There's one called double. Right? And these things approximate real numbers in Java. Okay? So double is what you would find in Python. But Python confusingly, well, all right, so Python and Java, they both have a type float. But in Python, Python's float is Java's double. Java's float doesn't correspond to anything in Python. Double is wider than float in Java. So a double can hold a wider range of numbers than float. Now, all the weirdness with floating point math happens because of the next line, right? So everything I'm about to talk about is caused by this one line, right? On the computer, you've got a fixed finite amount of memory, right? And these values, float and double, they occupy a fixed amount of memory, right? Now, if you think about it for a second, if you have a fixed amount of memory, there's no way you can represent every real number exactly, right? Because most real numbers, like the vast, vast majority of real numbers, have an infinite number of digits, right? So there's no way I can represent all real numbers exactly. The strange part is you can't even represent the number 0.1 exactly, which seems really odd when, because we're used to the base 10 or decimal system. Right? So for most of us, it's natural just to write, 0.1, 0.1, 0.1, add them together, and you should expect to get 0.3, but the answer is you don't. Right? So on the next line, if you write x equals 0.3, the answer is false. If you use double, if you use float, the answer is true, which is even more confusing. Right? So why does all of this happen? Right? There's this little program here. If you run it, you will actually see what gets output by you'll see what gets output, or what the actual value of 0.1 is, right here. What the actual value of 0.1 plus 0.1 is, and so on and so on and so on. Right? I'm not going to run it for you now, because that would involve bringing up Eclipse and compiling it and cutting and pasting all that in, and so on and so forth. But if you run it, right, that line there does not print out 0.1. It prints out 0.1, 0, 0, 0, so I think there's like 15 or 16 zeros, and then there's some more digits. Right? That does not print out 0.2. It prints out 0.2, a bunch of zeros, and then some more digits. Right? Same with same with that one. Right? So that doesn't print out 0.3. That doesn't print out 0.4. Oddly enough, the last one does print out 0.5. Right? And 0.3, well, that's not 0.3 exactly either. Right? It's 0.3, a bunch of zeros, and then some other digits. So this is using the class called big decimal in Java, which we don't really use in this course at all. Big decimal is what's called an arbitrary precision floating point value. Right? That is, you can tell it how many digits it should store. Right? So you're able to store many more digits than float or double if you so choose. Right? Okay. Now, when you run that program, hopefully you run that program at some point in time, right? You have to be a little bit careful about interpreting the output. Right? So a double value, if you convert that value to decimal, right, so base 10, you only get between, you get between 15 and 17 significant digits, right? But when you run that previous program, you get a lot more digits printed out. Okay, so that you have to be careful about that. It's not true. You don't get like the 64 digits that thing prints out. I think it's 64, 32 or 64. It prints out a lot, right? So what's happening is Java is taking that number 0.1, right? It's converting it to the nearest double value that it can represent, right? So that 0.1, I told it, when you write down the literal 0.1, that's a double, right? So it takes that 0.1, converts it to the nearest double value that it can represent. Right? Now, the computer uses base 2 binary, right? Not base 10 decimal. Right? So what the program ends up printing out is the result of converting that base 2 number back to base 10. Right? And that's not 0.1. Right? That's when you get that long stream of digits. Okay? So you have to be a little bit careful, right? You should remember that a double has roughly 15 to 17 significant digits. So there's something called the IEEE 754 standard, which almost every desktop computer uses now. Right? Your desktop, your phones probably use it. Smaller embedded devices may or may not use it. Okay? So that is the official standard for floating point arithmetic used on most modern CPUs, intended for general purpose computing. Right? Now, it's a huge standard. Very few people understand it completely. What you need to know, right, is that every floating point number has the following form. Right? You can write it like that. So plus or minus s, right? So plus or minus positive and negative values. S is an integer, right? So it's some integer value times 2 raised to some integer value. And that thing e may be negative. right? So that's how you get values less than 1, is if E becomes negative, right? That thing S, that's called the significand. If you're reading an older reference, you might see it called the mantissa, but it's the significand nowadays. E is the exponent, right? They're both integers, right? So everything's an integer on your computer, right? Because everything's binary. It's all zeros and ones. OK, now, why is 0.1 0.100000000, and then some extra digits, right? So you can't represent 0.1 exactly in floating point, right? The proof is here. It's also in the notebooks if you're reading the notebooks, right? So I just told you I can write every floating point number as s times 2 to the e, right? So I'm going to assume that I can find some value of s, some value of e, such that that expression is true, right? And so now you say, well, can I find s and e such that that value is true, right? OK, so you just multiply both sides by 10, right? 10, 10, that gets rid of the 0.1, right? So I now have 10s times 2 to the power e is 1, right? OK, so let's divide both sides by 2 to the power e, right? So I get 10s is equal to 1 over 2 to the power e, right? And then you know that 1 over 2 to some exponent, I just negate the exponent, right? So I can write that as 10s equals 2 to the minus e, right? And that's a contradiction, right? E is an integer. S is an integer, right? In this case, e is also negative, right? So that's 2 to some positive value, right? So if I write that out, that's 2 times 2 times 2 times 2 times 2 times 2 e times, right? It's all 2's on the right-hand side. The left-hand side is 2 times 5 times something, right? So you've got a 5 on the left-hand side. You've got a bunch of 2's on the right-hand side. Everything's prime, right? 5's prime, 2's prime. So there's no way you can write 10s equals 2 to the minus e, right? Because the prime factorization of the left side has a 5. Prime factorization of the right side has only 2's, right? So there's no way to get a 5 on the right-hand side, right? And there's your contradiction, right? You cannot find values, integer values, s and e, such that that equation is true, right? So you can do this exercise for whatever values you want, right? If you do 0.5, right? So if I change 0.1 to 0.5, right? The answer should be obvious, right? 0.5 is just 1/2, right? So if I choose e equals -1 and s equals 1, it's like, oh, I can write 1/2 in floating point exactly, right? And that's why the program that I showed you earlier, when you ask it to print out 0.5, it actually prints out 0.5. Right? Because there is an exact there is an exact binary representation of 0.5. OK, so that's why you can't get 0.1. Now, the value you get is awfully close to 0.1, right? The difference is way out in the 15th or 16th digit after the decimal place. So it's not like the error is massive, right? It's actually very small. But still, you can't represent it exactly. OK, now, these float and double things, these are actually 32 and 64 digit numbers, right? They're binary, so they're all zeros and ones, right? I don't want to write out 32 and 64 digits every time I try to write down a number, okay? I also don't want to work in base 2, because I'm no good in working in base 2, and I'm pretty sure neither are you, right? So instead, I'm going to switch to decimal, and instead of 32 and 64 digit numbers, I'm just going to use 4. Right? So I'm going to use 4 digits. And this slide tells you how, well, it tells you approximately how floating point numbers are actually represented on your computer if your computer used base 10. Right? So if your computer, so I'm only using 4 digits, right? 4 digits between 0 and 9. Your digits are D1, D2, D3, and D4. Right? So they're your digits. Right? The digits in front here, D1, D2, and D3, those make up S, right, the significand. So there's your integer that I'm going to multiply by 10 to some exponent, right? My last digit is used to define the value of the exponent, right? And then I subtract 5 from that, right? Now the reason I'm using exponent, the reason why I'm subtracting 5 is so that I can get negative exponent values as well as positive exponent values, right? Without having to also store the sign of the exponent, right? Notice here I'm storing the sign of the significand, right? On your computer, that actually costs you 1 bit, right? So that takes up one of the digits that you're using to represent the number, right? Because bits are 0 and 1, right? So to represent plus and minus, I need 1 bit. So I actually lose a bit. I don't want to lose another bit when I define the exponent, right? So by subtracting a constant amount, right, that 5 in this case is fixed, right? That gives me the ability to get negative exponents and positive exponents at the same time, right? That 5 is called the bias. Right, so every number that I write in base 10 is going to be written like this. Every floating point number that I write in base 10 for today's lecture will be written like this. Okay, so let's take a look at some examples. Right? Oh, wait, there's one more important thing. D1's not allowed to be 0. Right? So I'm not allowed to have, that significand cannot contain leading zeros. Right? So you're not allowed to have, so you should think about what happens if you allow leading zeros. But I'm going to skip over that for now, right? So let's look at some examples, right? Here's my 4-digit number, right? 1, 0, 0. There are my first 3 digits, raised times 10 raised to the power minus 5, right? And so in this case, my exponent is D4 is actually 0, right? 0 minus 5 is minus 5, right? You know what the decimal value is. I don't have to tell you. You can convert that to decimal, no problem, right? Now, remember, I only get 4 digits, right, to represent these numbers. So the next decimal number that the next floating point number that I can represent is 101 times 10 to the minus 5, right? I can't represent any values between these two, right? Because I don't have the digits to do it, right? I only get 4 digits. So the decimal value of that is 0.00101. If you look at the difference between those two, right, that's a difference in the 5th digit past the decimal point, right? So 0.00001. Right, you just subtract the second one from the first one from the second one. Right? So let's look at another example. So now I'm going to change the exponent, right? I'm going to go up by 1 order of magnitude. Right? So the next, the smallest number that I can represent that's raised to 10 to the minus 4 is 100. Right? Its value is 0.01. Right? Now remember, I only have 4 digits, right? And I only get 3 in the significand. So the next number that I can represent is 101 times 10 to the minus 4. Right? And that's 0.0101. Notice the difference here, right? Is 0.0001. Right? That's different than from the previous 2 rows. Right? So the spacing between adjacent floating point numbers changes depending on the value of the floating point number. Right? When the exponent's minus 5, I can represent numbers to within 0.00001. As soon as I go up 1 order of magnitude, I lose one of those digits of precision. Right? So now I can only go to 0.001. Right? If I go way up to the largest exponent that I can represent, right? So that's 4, right? The smallest floating point number I can represent, written this way, is 100 times 10 to the 4, right? And that's 1 million. Yep, that's 1 million. Right? The next number that I can represent is 101 times 10 to the 4, right? And that's 1,100,000. 10,000? 10,000. 1,010,000. Right? Now the spacing between numbers is 10,000. Right? I can't represent anything between those 2 numbers. Right? I can't represent anything between those 2 numbers. I can't represent anything between those 2 numbers, and I can't represent anything between those 2 numbers. Right? And that's why there's a whole bunch of numbers that you can't, real values that you can't represent in floating point. Right? Has everybody got that? That's very strange if you're used to working with real math. Right? I'm telling you that the spacing between adjacent values changes, right, depending on the magnitude of the value. Right? Okay, So what is that distance? So the distance between adjacent floating point values is something called the ULP, the ULP, right? That's the unit in the last place, right? Why is it the unit in the last place? Well, it's because the difference is the difference in the unit in the last place, right? So the difference between these two numbers is just the difference 1 minus 0, 5 places out to the right of the decimal point, right? Here, right, and it's the unit in the last place of the significand, right? It's not the unit in the last place of the number, right? So really, you need to look over here, right? So the difference, or the spacing between adjacent numbers when the exponent is 4, right, is 1 times 10 to the 4. Okay, so that thing there is called the ULP, and that's what's used for measuring errors in floating point values. Right? So for example, when I convert 0.1 to a floating point value, I can measure that error in ULPs. Right? It's very small. It's also a 64-bit. It's also a 64-bit number, so it's hard to express. Okay. Now, if you want to know how big an ULP is, you can ask Java how big the ULP is. Right? In the class Java Lang Math, there's a method called ULP. Right? You give it a value d, and it tells you what the unit in the last place is for that value of d. Right? Now remember, the numbers you're going to get back are strange because they're actually, because everything's encoded in base 2. Right? So it's not going to be some nice number like here. Right? Here it's always some power of 10. Right? Back here it's always going to be some power of 2. So you have to be, so when you see the value of ULP, don't be surprised if it's not anything that looks sensible to you. Right? Okay. Absolute error, right? So absolute error is defined as the absolute value of x hat minus x. Okay? X hat is the true value of whatever it is you're trying to compute, right? X is the actual value after you compute the value, right? I guess if you're a scientist and you're measuring things, right? X is the measurement, x hat is your expected value, right? Okay. When I convert any real number, right, that fits into the range of the floating point type, right, then I know, at most, the error is half an ULP, right? So the error is half an ULP. Okay, so let's go back to this slide here. So I've got here the numbers 10,000 and 10,100, right? Suppose I have the real value 10,000.1. Right? When I convert 10,000.1 into this floating point representation, right, I get 10,000. Right? My error is 0.1, 3 digits past the last red digit. Right? So you're going to see in a second that error in ULPs is 0.001. Right? You can get an error of 1/2 an ULP if you try to convert the number 10,050 to a floating point number, right? 10,050. So halfway between these two values, right? When I'm halfway between those two values, right? When I convert the floating point, I have to pick one of those two values, right? So I round to one of these two, right? And my error will be half the distance between those two, right? And so that's how you get a 1/2 ULP error, right? But you're always guaranteed to be within half an ULP. Okay, now how do you compute these errors? Right? So the ULPs are defined based off of the based on your floating point type. Right? So here I've got 3-digit significands. Right? So when I write x hat, I have to write that as a 3-digit significand raised to some exponent. Right? So I have to convert x hat into my floating point type. Right? You then write x also as a floating point type, because that's the value you just computed, so it's floating point anyway, right? And you use the same exponent as x hat, right? Because I need to measure the difference in that last digit of x hat, right? And then you just compute x hat minus x, right? Using the values in steps 1 and 2. Okay, this is actually not as hard as it's not very hard to do, right? So here's 1.29 and 1.25, right? Write them both as floating point numbers. Right? So 1.29 is 129, times 10 to the minus 2, right? 1.25 mine is 125 times 10 to the power minus 2, right? The exponents are the same, right? That exponent and that exponent are the same. So all I have to do is subtract 129 and 125 to get 4 ULPs, right? So this is the easiest example that you can do, right? Both the true value and the computed value, when you convert them to floating point, they have the same exponent. Okay, if they don't have the same exponent, you have to do some math. Right, so here 112.1 is 121 times 10 to the minus 1. Right? Now 0.5 is actually, 0.5 is actually in our floating point representation, right, 0.5 is actually, now remember I'm going to use 3 digits for the significand, and the first digit's not allowed to be 0, so the 5 has to go there. Right, so that's 500 times 10 to the minus, what is it, times 500 times 10 to the minus 1, 2, 3, right? Okay. But I have to now convert that to use the same exponent, well, so wrong computer, to use the same exponent as the first number. Well, so wrong. Right. So that's why it's written as 5 times 10 to the minus 1 here. Right? Remember, I'm trying to compute the difference in the last digit of the two numbers, right? The last difference in the significand of the two numbers. Right? And that's 116 ULPs, which is quite large, right? Quite large. Right? So I'm 116 floating point values away from the true answer in this case. Right? Now, sometimes you've got a problem where the true value, you know it as a real number, right? So for example, pi, right? If I'm trying to compute pi on the computer, the true value is pi, and that has an infinite number of digits, right? You handle it in exactly the same way, right? So you convert your true value to floating point, but you only keep, but you have to make sure that you have 3, in this case 3 digits in the significand, right? And then you just keep everything after the decimal point. Right. So here I've got the number 592.87.5603, right? There's way more than 3 significant digits here, right? So I convert that to floating point, right? So that's 592.875603, right? Now, if you were to really do this on your computer, you couldn't keep the 875603, right? Because I don't have that many digits in the significand. Right? But for the purposes of computing error, you keep them all, right? Even though I can't actually represent that using floating point. 58,900 is just 589 times 10 to the power 2. Right? So that's easy, right? Subtract away, you get 3.87 times 10 to the 2, right? So 387. But that's actually only 3.87 ULPs, right? So you're roughly 4 digits away, 4 numbers away from the true number, 4 floating point values away from the actual answer. Right? Any questions so far? Right? When you do this, all you have to do is make sure that these exponents are the same. Right? The way I've described it, I think, is the easiest way to describe it. As long as those exponents are the same, though, it doesn't actually matter how you do the conversion. Right? Okay, relative error. Relative error is just the absolute error divided by the true value. Okay? And you don't bother with this conversion to floating point. You just take your values, plug it into the equation, and crank it out. Okay? So when you go to compute, if someone asks you to compute the relative error, you just compute the value of that equation. Right? The notebooks has lots of examples. All right. So that's what happens when you convert some number, a real number, to a floating point number on your computer. Right? We know how to measure the error in that conversion, right? Or in, yeah, so I'll just leave it at that, as in that conversion. Now the question that we have now is what happens when you start doing arithmetic with floating point values, right? Now remember, this is all messed up because I've only got 3 digits in the significand, right? So when I'm adding and subtracting things, funny things are going to happen, right? So to add or subtract two values where they have the same exponent, life is easy, right? So you just convert those two numbers, right, to their floating point representation, right? So 12.1, 121 times 10 to the minus 1, right? 63.8, 638 times 10 to the minus 1. Exponents are the same. Add the values, you get 759 times 10 to the minus 1. Right? Easy peasy. Next example, exact same thing. Right? 81,500. Well, that's just 815 times 10 to the 2. Right? 13,600. That's just 136 times 10 to the 2. Exponents are the same. Everybody's happy. Add everything together. Away you go. Right? Still have 3 digits in the significand. Still have 3 digits in the significand. Don't have to change the exponent. Don't have to change the exponent. Right? Things get only slightly more complicated when you're adding things and you end up creating a new digit. Right? So obviously, if these two numbers here are bigger than, if they sum to something value bigger than 1,000, right, you get a 4th digit. Right? Now, I only have 3 digits in the significand, right? So I have to decide what I'm going to do here, right? So for our purposes, I'm going to do the simplest possible thing, right? I'm going to say, well, we'll just keep the 4 digits, right? Even though I don't actually have 4 digits, right? I have 3, right? We'll keep the 4 digits, compute the result, and then round to the final answer, all right? So do the conversion, right? 82.1, 821 times 10 to the minus 1. Right? 63.8, 638 times 10 to the minus 1. Add them together, right? 4th digit appears. OK, that's fine, right? Just do the sum anyway, right? So we get 1459 times 10 to the minus 1, right? Now take that number and convert it back to your actual floating point representation, and we're going to round the answer, right? So 1459 times 10 to the minus 1, when I round it, is just 146 times 10 to the 0, right? So notice the exponent goes up by 1, right? And if you think about it for a second, the exponent will never go up by more than 1, right? And you will never get 2 digits in the front here if you add 2. You'll never get 2 extra digits if you add 2 numbers, right? You're always creating at most 1 extra digit. The exponent always goes up by 1 at most, right? Another example here, it's the exact same thing, right? The intermediate result is 1751, right? I have to round that to 3 digits, so it becomes 175.1 times 10 to the 3, right? Round the 175.1 to the nearest integer, and that's 175, right? And away you go. OK, so I'm keeping the extra digit when we're adding things together, and the sum causes the order of magnitude to change, right? OK, now, here's where things really get strange. If the operands have different exponents, right, then you take the operand with the smaller exponent and scale it so that it matches the other exponent, right? So 4320000, 4.32 million, right? That's 432 times 10 to the 4. 12.1 is 121 times 10 to the minus 1. Right? But I now have to scale it so that the exponents match. Right? So when you do your scaling, you get that. Right? Which you can easily confirm by doing a little bit of arithmetic, by doing a little bit of math. Right? Just move the decimal place 4 digits over to the right, you'll get 12.1. Right? Compute the intermediate result, keeping all the digits. Right? So you get 432.00121. And then round to 3 significant digits. And notice what has happened here, right? When I take a number and add another number to it, add another non-zero number to it, right? I get the original number, right? In other words, right, x plus, whoops, I have the x plus y is equal to x, where y is not equal to 0, right? Which is strange mathematically, but that's what happens when you have floating points, right? Why does this happen? Because I can't represent these digits, right? I only get 3 in the significand. Right? So there's no way for me to represent those digits when I go to compute the result on the computer. Right? So I actually, to actually compute this sum correctly, I need an 8-digit significand, right? But I don't have it. I've got 3. Okay, now, using these extra digits is not always feasible in computer hardware. So it certainly wasn't feasible back in the, well, it certainly wasn't affordable back in the 70s and 80s. Right? You might say, well, look, I know some of these values are going to, to compute some of these values, I know I'm going to need extra digits, so why don't I just use some extra digits? Right? Because it turns out in hardware it's very expensive. Right? Or at least it was. Right? Today, computers do use extra digits. But in the past, it wasn't. Right? So, right, when I compute this thing, right, so I just told you keep all the extra digits, right? But now let's suppose that I can't keep those extra digits because I only got 3 digits in the significand. So now, when I scale that second value, I'm going to throw away everything that's past the 3rd digit. Right? So here, instead of keeping all 8 digits, I'm just going to toss everything that's after that 3rd 0. Right? And you get the same result. Right? So I'm effectively adding 0 to 4.32 million in this case. Right? Now, if you don't use extra digits, addition and subtraction can produce very large errors. Right? So here's 10.5 and 9.98. Right? Those are not very far apart. Right? Mathematically, they are only 0.57. Right? There's a distance of 0.57 between those two numbers. Right? Very small. What happens when I subtract them? So 10.5 is 105 times 10 to the minus 1. 9.98. Right? So now I'm going to toss everything after the 3rd digit. Right? So when I convert 9.98 to have the same exponent as the first number, right? That's going to be, I want to write 99.8. Right? That's what I want to write, 99.8 times 10 to the minus 1. Right? But I have to now discard that 0.8. Right? So out goes the 0.8. Subtract. You get 6 times 10 to the minus 1. Right? Convert that back so that the first digit's not 0. Right? You get 600 times 10 to the minus 3. Right? The true answer is 0.52, right? Which is 520 times 10 to the minus 3, right? That's an error of 80 ULPs, right? You're 80 numbers off compared to what you should have gotten, right? The standard says you have to be within 1/2 an ULP for any basic operation, right? So multiplication, division, addition, subtraction. The IEEE standard says when you do this, you must be within 1/2 an ULP, right? And here, I'm at 80, so this is no good. Right? So obviously, we're not going to do it this way. OK, so I'm going to do the same thing that I did for addition. I'm going to say, well, let's introduce a 4th digit. Right? These are called guard digits. Right? So I will keep 1 extra digit after the decimal place. Right? So I'll keep 1 extra digit. So now I've got a 3-digit significand, but there's an extra digit after the decimal place. So I now effectively have a 4-digit significand, right? But you're going to write it using only, but you're going to make sure that you only use 3 in the front, right? So you can't move that decimal place around, right? So 3 digits in front, 1 extra digit after the decimal place, compute everything, right? So now when I do the calculation, I get 5.2 times 10 to the minus 1, right? Which is, in fact, the correct answer, right? That's the true difference. So good. We're within 0 ULPs, right? Perfect. So it turns out you can't guarantee the 1/2 ULP with only 1 guard digit, right? You need at least 2. So for example, I take 110 minus 8.59, right? Crank through all the math, right? You get to 102 times 10 to the 0, right? If you actually compute that true difference, that's 101.41, right? 101.41. Here I get 102, So my error is 0.59 of an ULP. So I'm not quite within that 1/2 ULP error bound. Right? So it turns out you need a second guard digit in this case. I believe on Intel computers, the doubles are 64 bits, but Intel computers will compute them using 80. So there's effectively 16 extra bits that they're using for something. Right? So 16 extra binary digits. So the situation is not so severe on a modern computer. Right? But in the past, it was really expensive to make these CPUs. Right? And there was no way that you would, if you asked somebody to throw in some extra bits, they'd just laugh at you. Right? OK. What time is it? I guess I can start this. Subtraction is especially problematic with floating point numbers. Okay? So when you subtract two different values, right? There's usually not a significant error in the answer. The problem happens when you subtract two similar valued numbers, right? And so what happens here is what's called cancellation or loss of significance, right? So here I'm going to temporarily use 10-digit numbers, okay? So here I've got this big number 1 through zeros times 10 to the 0, right? And then I've got the very similar number, right? It's off by 1 in the last digit, right? So when I subtract them, right, what happens, right? All of these significant digits, right? I used to have 10 significant digits, right? But now the first 9, they're gone. They're all zeros, right? So when I renormalize this number, right? In other words, when I get rid of all the leading zeros, I end up with 1 and then a bunch of zeros times 10 to the minus 9, right? So the difference, right? That value of x minus y only has one significant digit. Right? There's only one digit there that's not 0, right? Even though my inputs had 10, right? I just lost 9 significant digits in my operation. That's going to be a problem, as you'll see in a second. Right? Now, why do we call it cancellation? Because the leftmost bits got canceled, right? When you do the difference, right, all these bits on the left-hand side, or sorry, all these digits on the left-hand side, they go away, right? They cancel with one another. Right? So those leftmost digits, those are called the high-order digits or the most significant digits, right? They're the ones that matter the most in the final value of the answer, right? Because they're the largest, they have the largest magnitude. The digits on the right-hand side, those are called the low-order digits or the least significant digits. Right? Notice when I do the difference, I'm stuck with the least significant digit. Right? I'm stuck with all I get is the digit that mattered the least in the final answer. Right? Now, okay, so when you subtract two values, right, and those two values, they don't contain any significant round-off error. Right? In other words, there are two values that, so for example, you might type in two values, right? X equals 0.1. and y equals 0.09 or something like that, right? Those values are as close as they can be to their, so when you type those in and convert them to floating point, those values are as close as you can be to 1 and 0.9. I hope those are the two numbers that I used, right? Then it doesn't matter. When you do subtraction, you get the answer to within half an ULP, right? So that's called benign cancellation, right? Yes, cancellation happens, but the answer is still more or less correct. The problem is what happens when you compute x and y, and then you subtract x and y, right? Now, when you compute x and y, right, your computation introduces error when you compute x. Your computation introduces error when you compute y. If I subtract these two values and they're close in magnitude, that's when you get what's called catastrophic cancellation, right? So catastrophic cancellation occurs when one or both of the operands contain error, right? So for example, when you compute the operand before you compute the difference, right? So here is b squared minus 4ac, right? That's part of the quadratic formula, right? So you can imagine that this is used quite a lot in some applications, right? Anywhere you have to find the roots of a quadratic equation, which turns out is quite a few places, right? So b squared, well, I have to compute b squared. Presumably I know b, right? But to get b squared, I have to compute it. Presumably, I know a and c, but to get 4ac, I have to compute that. Right? So what happens when you do this? Right? So if I choose b equals 3.34, a equals 1.22, and c equals 2.28, if I compute the exact value, I get 0.0292. Right? You just crunch through the math. It's, there's nothing interesting here. Right? I get that number. Now, what happens when I compute this all in floating point? Right? So, what's b squared? Well, b squared, the true value is 111.556 times 10 to the minus 1. Right? Now, we don't know how to do multiplication, right? So we don't actually know how we're going to do it. So I'm just going to say, look, just compute it using regular multiplication and then round the answer. Right? That turns out to be actually the best case scenario for floating point. Right? So I'm going to round that to 112 times 10 to the minus 1. Right? Why 112? Because I only have 3 significant digits in my floating point system. Right? 4ac is 111.264 times 10 to the minus 1. So compute it exactly, round the answer, 111 times 10 to the minus 1. Right? Now I can compute the difference using my floating point values, right? And my difference is 0.001 times 10 to the minus 1, right? Which is 100 times 10 to the minus 3, right? 100 times 10 to the minus 3. True answer is 292 times 10 to the minus 4, right? None of my digits are right, right? The 1's not right, the 0's not right, the 0's not right, and the exponent's not right. Nothing's right, right? It's completely wrong. If you compute the difference in ULPs, it's 708 ULPs, right? It's enormous. That's no good, right? That's an extreme example of catastrophic cancellation, right? It's an extreme example here because I'm only using 3-digit significand, right? Obviously, on your computer, you have much larger significand. So if you use these same numbers, you'll get a much smaller error, right, on your computer, right? But you can always cook up values where when you do this subtraction, you get a completely wrong answer, right? In other words, catastrophic cancellation makes your final answer completely useless, right? Sometimes you can avoid it, right? And so the way to avoid it, you can sometimes avoid it if the equation that you're computing, you can transform it somehow. Right? So that often involves some sort of trigonometric or exponential transformation of some kind. Right? It turns out you can transform the quadratic equation in, there is a way to transform the quadratic equation to avoid this cancellation. Right? So sometimes you can do this. Now this isn't a math course, so I'm not so concerned about showing you examples of how to do this. Right? But the notebook does tell you how to, does give you some examples. Right? So if you read the notebooks, you will see examples of how you can transform some equations, right, to avoid the catastrophic cancellation. Right? One of the examples is there's some equation that if you compute it using double, on your computer, you get 0. But the true answer is actually 0.5. And so that's no good either, right? But when you transform the equation that you're computing, you actually get the correct answer. OK. I guess I should stop there because it's 1/4 and you guys need to get out of here before the next class comes in. So I'll pick up from slide 31 on Wednesday.